Okay, so first video in a little while for you guys. It is currently evening, it's very, very dark outside, and I'm here today to talk about torque and rotational dynamics. We've talked about torque a little bit in class the week before break. You kind of got your feet wet with it. We're going to see some more of how torque can apply to systems, and you're going to groan because you're going to look at me and you're going to say, wait a sec, you lied to us about something else. And I did, okay, in the idea that we wanted to simplify dynamic systems that involve forces, systems that involve motion. We simplified it because we didn't want to deal right in the beginning of the year with objects that have torque acting on them. Now we're going to deal with that, okay? And I think, we are complicating things a little bit, but you are also seeing something that's a lot closer to what actually happens. We were leaving out, a fairly big chunk of what happens, which is fine if you want a first approximation, but now, as you guys have done more and more physics, you've gotten used to this, we're going just a little bit deeper into it. And so, actually, let's just get started. I'm thinking between the notes and the one tutorial that we'll do, this will probably be, I'll try and go as quick as I can with still being understandable, thinking about 4 to 5 videos for this. And then rolling, I haven't even thought about. I'll probably come back tomorrow morning and do rolling. Okay. Anyways, with torque and rotational dynamics, before we get into what this really means, quick review of torque. You should know what this is. A torque is very simply a rotation of an object caused by a force being applied to it. Okay. When we first dealt with forces, they caused objects to translate. They caused them to move in either a line or a curved path. Now we have an object that has a force on it, and it's not just being caused to move, like from a certain position, it's being caused instead to rotate. Okay? The size of the torque, or the magnitude of the torque, is affected by 3 things. Number 1, magnitude of the torque is affected by the magnitude of the force. Okay? It matters how hard you push on something and try and make it rotate. Kind of obvious. Another thing that matters, the distance that the force is applied from, and I'm going to abbreviate to save some time, axis of rotation. Okay, this is R in the torque formula. We remember the torque formula is, that's a tau, it's a really bad tau, equals R, F, sine theta. Okay, this is the R. How far away is the force from the axis of rotation? That is something that matters. The third thing has to do with that theta. Angle between the previous 2 factors. Okay, the angle between that force and the vector that goes from the axis of rotation out to where the force is applied. That is what the 3 things that the torque depend on. Let's see, torques. They can either cause clockwise or counterclockwise rotation. So 2 different ways that they can cause something to rotate, clockwise or counterclockwise. Typically, counterclockwise is positive, but that's just a general convention. It's like saying up and right is positive. Yeah, most of the time it is. You can set it whatever way you want. And then finally, the equation that kind of links torque and force. We know that with forces, if you want to know the overall effect of something, you add up all the forces that are acting on an object in a specific direction. And that's equal to the net force, which is equal to M times A. The net torque, very similarly, is equal to the sum of the torques, whether they're positive or negative, and in turn that is equal to I alpha. I being something called the moment of inertia, which we'll talk about in a little bit, alpha being the angular acceleration. Okay? That's, in a nutshell, everything you learned about torque. Angular motion, we talked about right before we talked about torque. Angular motion is not very difficult. If you know anything about linear motion, which you all do, it was the first unit that we did, then you know the exact same things about angular motion, okay? It is the same exact equations as linear motion, but with angular variables. That's what I call them. So we'll just get a little list going off to the side here. Here are some equations that you knew from linear motion. You know that V equals d over t, speed equals distance over time. Well, these are all linear variables, I guess time isn't, but when we talk about angular variables, this transforms into angular speed, this is an omega, or you can call it a wumbo, equals theta, the angle something rotates through, over time. We also have, here's the fiat equation, or whatever you want to call it, V equals V naught plus AT. We just translate it to angular variables. It works exactly the same. The initial, or the final angular speed of something, the final speed something rotates, is equal to the initial speed that it rotates at, plus alpha is angular acceleration, same as up there, multiplied by time. Let me just write the other ones down for you. X equals x naught plus v naught t plus 1/2 at squared becomes theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And finally, v squared equals v naught squared plus 2a x minus x naught will become omega squared equals omega naught squared plus 2 alpha theta minus theta naught. Okay? There are three other equations that we talked about that relate the linear variable to the angular variable in all three of these cases. The only one that's a little tricky, well, it's not even tricky, you should know this from math class, okay? S is like a linear distance. You could really call this is really like D, okay? S is a linear distance. The linear distance that an object travels is equal to the radius of the circle. We're talking about rotational motion after all. Radius of the circle that it's rotating around, and how big of an angle it rotates through. V equals R omega. The linear speed is equal to the radius times the angular speed. The linear acceleration is equal to the radius times the angular acceleration. And the units, okay, the most important one is instead of measuring things in meters, we measure things in angles here. Every one of these variables, theta, omega, alpha, they all have radians in them somehow, okay? These angles, or just angular quantities in general, are measured in radians, okay? This is the one unit where you need to have your calculator in radians. No, you don't. No, you might. But you need to be thinking in radians. This is not about degrees, okay? We are talking purely about radians. Torque review, angular motion review, okay? Those are two topics that we've discussed fairly recently. Here's another one, actually. Moment of inertia, which I've mentioned, and I feel like I probably kind of glossed over it. We're going to get way into the weeds with moment of inertia. Actually, you don't have to know as much as you used to have to know about it, moment of inertia, but it's still kind of a weird topic. Hope everyone's having a good break so far. I know I have had a pretty good break. Okay, moment of inertia. Moment of inertia is very similar to mass. Matter of fact, mass is in the equation for calculating a moment of inertia. You do need to know the object's mass. Mass is how hard it is to get something to translate, to move from one place to another. Moment of inertia, on the other hand, is how hard it is to get something to rotate. How hard it is to rotate something. And this is based on two things. It's based on the object's shape, and it's based on the object's mass. I gave you the demonstration of it's very easy for me to rotate the window screen that's in the back of the room. very easy for me to rotate the window screen in a certain direction because the mass is fairly close to the axis of rotation. If I try and rotate it a different way, the mass is not all close to a different axis of rotation. It's much, much harder. I was able to do one with one hand. I was not able to do another with just one hand. Okay? So it depends on the shape of the object. Also depends on the axis of rotation. Okay? It's a lot more complicated. We're going to talk about some specific moments of inertia right now. Let's talk about the moment of inertia for a point object. This is an object that you can treat as essentially one little point in space. We're going to treat it, so a point itself doesn't rotate, okay? Think of an electron. Electrons don't rotate, okay? They don't spin around. What we're talking about when we say I for a point object, we're talking about a point object of mass m revolving the distance r from its axis. So, a couple examples. Imagine, let's say, a tether ball. You guys hopefully know what a tether ball is. A tether ball, it's a ball, you could treat that like a point object. It's revolving around a central axis. It's revolving around the giant pole that it's tethered to. Another example of a point object would be, let's say, like a planet revolving around the sun. The axis is through the sun, and the planet revolves around it. You could treat that like a point object. Now, the moment of inertia, for these types of objects, for a point object of mass m revolving a distance r from an axis, is as follows. I equals m r squared. This is the only formula you will have to memorize for moment of inertia. A point object of mass m revolving a distance r from its axis is I equals m times r squared. That is a formula for moments of inertia for that particular case. Okay? For any other shape, for an object that's rotating about a central axis, for like literally anything else, you don't have to memorize. Okay? For all other shapes, the formula looks like this. I equals a times m times r squared. And a is not acceleration. Okay? A is a coefficient. A is some coefficient. Obviously, m is the mass, and r being, I'm just going to call it some important distance. So, for any other shape, let's say you have a cylinder that's rotating, or an actual sphere that's rotating on an axis that's through the sphere, or you have, I don't know, literally anything, okay, a hollow cylinder, a solid cylinder, a hollow ball, a hollow disc, a hollow tube, a hollow, like a hoop, okay? Any other moment of inertia equation will have this general formula. R is some distance that's important to that shape, usually like a radius or something like that, or a length. M is the mass. A is a coefficient, 1/2, 2/3, 2/5, 1/4, 1/12, something, okay? You do not have to memorize A for all these different objects. They will tell you what A is. Back in my day, they had you, well no, I think they had it on a reference table. You had to look up what type of shape it was. Okay? So, when you see different formulas in the next couple of days, next couple of weeks, do not memorize formulas for a moment of inertia except for the one for a point object, mr squared. They will be given. Okay, they will be given to you. You do not need to memorize them. The last thing I want to talk about with moment of inertia before we get into talking very briefly about angular momentum. I don't know why I talk about it here. You might even be able to... no, we'll talk about it very quickly and then we'll talk about it in class some more. Last thing with moments of inertia though. Let's say you have a complex object. Let's say you have an object with multiple parts. Maybe you've got 2-point objects, okay, that are revolving around some central axis. If you have a complex object, or an object with multiple parts, for an object with multiple parts, the total moment of inertia is just the sum. The normal old sum, you just add up the moments of inertia for each part. I tot is sum of I parts. Okay? So if you get, I don't know, let's say, like you have this example. You have a center axis, you have two, and I'm going to erase this in a second. You have two little point objects, they rotate around, out from the board, into the board, and out like this. You got two of them. You figure out the moment of inertia for one, you figure out the moment of inertia for another, you add them together, that's the total moment of inertia. Okay? That's pretty straightforward. Now, angular momentum. Really quickly. You see the word momentum in there. It is the rotational equivalent, just like so many other things in this big topic. Rotational equivalent of linear momentum. That's all it is, okay? You know linear momentum is this thing that objects have because they have mass and they have velocity. Angular momentum, same thing. It is this quantity an object has because it's moving and it's rotating around something. Actually, it doesn't even have to be rotating around something. It's moving relative to some axis. Okay? So, very quickly, and again, we'll come back to this in class. For a point object, for one little tiny object revolving around a central axis, here is the formula. Oh, angular momentum, the symbol, you're not going to like it. Sorry, it's capital L. For a point object, the angular momentum formula is mvr. Which is funny, Miss Valentine back in the day when I was taking AP Physics 2, she told us that if there's ever a question about angular momentum, MVR, that's all you have to know. And we all just looked at her like, what are you talking about? She's like, MVR, that's all you have to know. And we're like, okay. So I remember seeing a question that said angular momentum, and then I looked at the rest of the question. I said mass, velocity, radius. Cool, I'll just multiply all this together. And I got it right. Had no idea what I was doing, but I still plugged it in and I got it right. Okay? For right now, for an angular momentum for a point object, the mass times the velocity times r. You can even see m times v, that's like normal momentum. And we're multiplying that by r. Okay? The joke with angular momentum is, why is it called L? Well, it's funny that you mention that because there's actually a silent L in front of angular momentum. Okay? It looks like langular momentum. There's a silent L that we just stopped writing. I hope you know that's fake. Let me check our time real quick. I might have to stop. Yeah, I'll stop here.